The hypergeometric distribution is the next section we're going to be looking at. It's on the next tab here. And it's similar to the binomial distribution in that you have a success or failure that is defined. But what's different is there is no replacement, so the probability changes. For example, you're shuffling a deck of cards. As you're pulling out cards, the probability changes as cards are pulled out from the deck. So the example we're going to be using is, what is the probability distribution if there is a large bowl with 35 red and 25 blue gumballs or balls or whatever you want to call it, of selecting red? Okay. So we're going to find a couple items. N is the population size, N is the population for the success, and N is the sample size. So N is total population, so 35 plus 25 would be 60. Our sample size of successes will be the red, so that's going to be 35. And what is the probability of the sample size? Well, let's see. Let's say we're going to pull out 5 of them, 5 gumballs at a time. With that information, we go to our add-ins, our megastat, probability, discrete probability distributions. We'll go ahead and clear everything out. Go to our geometric. Our population size is 60. Our success is going to be 35, and our sample size is going to be 35 and 5. And push OK. All right. The probability of getting 0 is about a little less than 1%. Selecting 1 gumball that is red out of 5 is about 8%. Selecting 2 is 25. 3 is 36. 34, and selecting all 5 is about 6%. So we look at the graph, kind of goes up like this and down like that. So that is how we would find our hypergeometric distributions. Now understand that on the cumulative side, it is each phase or each step added on top of each other. So if you were to say, well, what is the probability of getting a 0, a 1, or a 2? Well, that's going to be a 34% chance of happening because it's adding all the way down. So that's a hypergeometric example. Now let's look at Poisson distributions. Okay. And this one is actually quite a bit easier than the other two because you're only needing one little bit of information, and that is the mean of the probability. But what is the Poisson distributions used for? Small likelihood with very large sample size, meaning something that is not going to happen very often. In the case that we're looking at, what is the probability distribution of a hard drive crash if the mean probability is 50%? Okay, so again, we go to our megastat, probability, discrete probability distributions. Clear everything out, go to my Poisson, and we say, okay, well, what is the mean rate of occurrence? Well, 15%, so 0.15. Now we can say if there's a maximum value, if we know it, we can put it in there, but it's not necessary, so I'm going to leave it blank and push OK. And it gives us a nice little output, meaning 86% of the time you're going to get 0 failures. Probability of having 1 hard drive crash, about 13%. 2 hard drives crashing, about 1%, and it just goes downhill very, very quickly thereafter, as can be seen with the chart. So really high probability of 0 not crashing, pretty good chance of 1, very low chance of 2, and it just gets minuscule thereafter. So that is the Poisson distributions. All right, now on to the uniform distributions. The uniform distribution is exactly that. It looks like a box. Fairly simple, fairly easy, where we have a starting point and an end point. These are the equations that we're going to be using. The mean is a plus b divided by 2. So a plus b multiplied by 2. Standard deviation is the square root of b minus a squared divided by 12. 12 is a constant in this case. It's always used in this point. And then the probability is 1 divided by b minus a. So let's put some numbers to these equations. The wait for a meal is uniformly distributed between 0 and 20 minutes. 0 meaning you get in right away. 20 minutes, you're waiting 20 minutes to get into the restaurant. Find the average wait time, standard deviation, and the probability of waiting 17 minutes. Okay, well, my A in this case is going to be 0. My B is going to be 20. So we can put this up here as well, 0 and 20 as a graphical reference. The mean is going to be equal sign. I'll go ahead and zoom in here a little bit more. Parenthesis A plus B divided by 2. Now you could type the numbers in, but if you were using this with a number of problems, you can just simply put in the A and the B in these numbers and the data will come out. And we push enter. So 10. No surprise there. Standard deviation, equal sign SQRT for the square root. And we're going to go ahead and set up a bunch of parentheses here. B minus A. Close that parenthesis. Now the little caret hat is from Shift 6, the Shift 6 button. Squared. Close that parenthesis. Divided by 12. Close parenthesis. And we push enter. So 5.77. What is the probability? Well, equal 1 divided by parenthesis 20 minus 0 minus a 0.05. Okay. So what is the probability of waiting 17 minutes? Well, since it is uniformly distributed, anywhere along this point we could say 17. Or any point would be 0.05 because it's the same exactly straight across. Now if we wanted to say, well, what is the probability of waiting between 17 and 20 minutes? Okay, well let's change it up just slightly. So P of X. So 17 to 20 minutes. Okay. Well, it's going to be an area problem. We're going to say, okay, well, 17 is going to be around here somewhere. We'll just say 17. And just for the sake of demonstration, I'll just color this little box in. Colored orange. We want to know the probability of this area. And it is exactly that, an area. So it's going to be base times height. The height is this px. The base is 17 minus 20. So, equal sign 20 minus 17 times 0.05. I'll just type it in this case to show the numbers. Basically, we're just finding the area of this box. And enter. So we have a 15% chance of waiting 17 minutes or longer for a meal at this particular restaurant. The next video is going to be looking at the normal distributions.